Okay, so today we will see how we will download data from Uniprot, so proteins, and we will use these proteins to build a phylogeny of a protein family. So our topic today will be protein family evolution. As an example, we will use the aquaporine protein family, and the general idea will be to download proteins from different organisms, having humans as a guideline, so to download the aquaporins of humans, and then find similar proteins in some other organisms. We will use mouse and chimpanzee, for example, but of course we can add additional organisms there, and then we will build we will make an alignment of these proteins and we will build a phylogeny. The goal will be to see how different aquaporine proteins from all these organisms are clustered together in the phylogenetic tree, because different clustering patterns will denote different evolutionary modes of this protein. We will see this. I will show in a sketch how this works, and then I will continue with downloading the data. Now, as I said, we will download some aquaporine data from 3 organisms. So let's suppose that we will have human, chimp, and mouse. So for example, the aquaporins of human will be denoted like human 1, human 2, human 3, and so on. I don't know how many aquaporins we will find there. And then we will have some for chimp, chimp 1, chimp 2, and some number of chimp proteins. It doesn't need to be the same between human and chimps, because due to duplications, organism-specific or species-specific duplications, the number of aquaporine paralogs cannot be different in different organisms. So let's put also some mouse example here, mouse 1, mouse 2, and so on. So if we will build then a phylogeny of all these proteins after we will download the FASTA data, then we might see the following results. So it might be that, it might be we will have the following possible scenarios. Scenario number 1. All human proteins are clustered together. So in the phylogeny of human here, chimp here, and mouse will be far away, of course, then all aquaporine proteins will be clustered here. So H1, H2, H3, and so on will be here, and the same with chimp, and the same with mouse. And another scenario, in contrast to that, will be that we'll have a set of branches here that will cluster together the aquaporins. So aquaporine, the human one, for example, will be together with chimp one, and then somewhere else will be the human 2 with chimp 2, and let's put also mouse 2 here, mouse 1 here, and mouse 2 here, and somewhere else will be mouse 3 and human 3 and chimp 3, and so on. So these 2 scenarios are totally different, and they mean a quite different mode of evolution between the aquaporins. In the first case, it means that in the common ancestor there was a single aquaporine. Let's write it as Aquaporine 1. Along the evolution time, one aquaporine was transmitted vertically from generation to generation to the common ancestor of human and chimp. So there was an Aquaporine 1 prime here, some mutations of course. And then independently here we had duplications of the human aquaporines and chimp aquaporines, and the same happened here in the mouse lineage. Which means that if we do a phylogenetic tree, all these aquaporines here have a common ancestor more recently than one aquaporine from human and one aquaporine from chimp, or one aquaporine from human and one aquaporine from mouse. In contrast, in the scenario 2, we had an aquaporine somewhere here, and then we had a series of duplication in these common ancestors of human, chimp, and mouse, and we ended up with Aquaporine 1, Aquaporine 2, and so on in this common ancestor. And then speciation started. So eventually what happened is that all organisms got copies of aquaporines from the common ancestor. But since duplication happened before speciation, then a version, different versions of aquaporines are more similar in the three organisms than the duplications themselves, because the duplications happen much before the speciation events. So such a scenario supports ancient multiplications of the genes, so ancient expansion of the gene family, whereas the scenario 1 supports recent expansion of the protein family independently within each species. It might be, of course, that we will have some recent expansions as well. For example, here it might be that we will have mouse 2 prime, mouse 2 prime prime, and so on, which will mean that we'll have an expansion within the mouse lineage here for this Aquaporine 2, for example. Okay. So these are the two scenarios, and let's see how to study it. So of course this lecture is within the Linux class, but of course we cannot do everything just by using Linux commands. And of course Linux is useful not only for as an operating system, but it's a very good operating system for building pipelines. So we will use bash scripts to merge all the steps of a pipeline together, but the particular steps will be either bash commands or Python or Perl commands. Okay, so let's see how to do that. Okay, so let's go to Uniprot now. We will download the aquaporins from human, and we will use a programmatic environment to do that. So of course we can put, I will show first how to do that from the web interface, and then how to do that from the command line. Okay, so here we are on the site of Uniprot, www.uniprot.org, and then we go to advanced, and we choose here protein name, and this will be aquaporine, and then here organism, and we will choose human. We see here that human is Homo sapiens, okay, and its ID is 9606, that's correct. And then we'll click search, and then here on the left panel we will go to annotation score 5, which so when a protein is annotated in Uniprot, it gets a different score depending on how much evidence there is for this annotation to be correct, and we will use the highest one, 5. So these are the aquaporin genes or aquaporin related genes in Homo sapiens. Now we can either select all of them and download them here, but we will not do that. So if I select all of them, I can really download them by pressing download button here. We will not do that. We will go to share, and then we will click generate URLs for API in order to get the URL and use this URL in a script. So this will be canonical FASTA. We don't need to have compressed results because they are not so many, and then we will click here generate URL for API, and this is the URL. Now if I go to the help pages of Uniprot, I can go here. So these are the API queries, and I can see at some point that there are some small scripts in Python using the request library to get queries. So if I copy this URL that I had before and I paste it, I will paste it here just to show how it looks like. It looks like that. So it uses REST to and HTTP codes to get a URL that I can use later on in Python to download the data. Now, if you will inspect a little bit the URL, it's a bit strange because it has this %28% protein name, and then %3a, and then %29, and then %20, and then %20, and then %28. And it's not very clear what these percentages are. But if we go to Google and ask for HTML5 encoding reference, we'll see that actually the %20 means space, the %28 means opening parentheses, and %29 closing parentheses, and then there is this %3a, which I think it means a column, and %3b, we don't have this, I think it's semicolon, and so on. Okay, so it actually this URL means that query equal to parentheses protein name, column aquaporin, close the first parenthesis, and then %20 should be %20 space, and space, opening parenthesis, organism ID, column 9606, which is the ID of human, close parenthesis, space, and space, opening parenthesis, annotation score, column 5, which is our score, and then close parenthesis. So what I did here is that this aquaporin and this organism ID and this annotation score, I put them in variables. So for example, protein name aquaporin here, the variable protein name, organism human, and later on, if organism equals human, I convert this organism ID, I create this organism ID, which will be 9606. Then the annotation score is 5. I create this URL using these variables now, and I do that because actually these variables can get names from the command line. So if I will modify the script, that is not very difficult to do, it's actually very easy. I can give these values to these variables from the command line so that this script can be a general script to download data for any organism and for any protein family. And then this loop here, this code here will download the data and it will save them in this file, which is called output file name, and it's created here, and it will be in this specific example aquaporine human.fa. Okay, this script can run like that. Python 3 with Python 3. It runs and it creates this file, and it's this one here. It's FASTA formatted with some ugly names, unfortunately, here, some specific characters. This pipe, for example. No, this is not a problem, but there are some parentheses somewhere, if I'm not mistaken, that phylogenetic programs do not like, and later on we will change. But anyway, we can get the data. So here we have (13) proteins. I use grep here with -c to count how many times I have this greater than in order to count how many data I have downloaded. Okay, this is the first part, that how to use Python and REST API and URLs to get data from Uniprot. We will continue with downloading the proteomes of chimp and mouse in order to ask for similar proteins in these two organisms. Similar, I mean, to the aquaporins that we have downloaded for humans. Then we will download these proteins as well, and we will build the phylogenetic tree. Okay.